Hi everybody, welcome to this video about molecular orbitals. So we'll talk about molecular orbital diagrams, and this is content that's covered in Organic Chemistry 1, but it will be helpful to have a refresher here. Now let's remember that molecular orbital theory, molecular orbital diagrams really help us understand where electrons exist within a molecule so that when more than one atom is bonded to each other, and the energetics of the different possible molecular orbitals, so where electrons can occupy, where they can exist in space. And we'll start with drawing the molecular orbital diagram for the dihydrogen molecule. Now remember, dihydrogen is a molecule that consists of two hydrogen atoms. If we think about what we already know about hydrogen, we know that it's in the first column of the periodic table. Being in the first column means that it has one valence electron. As an atom, individually, not as a part of a molecule, it has one valence electron. We also know that since hydrogen is in the first row, its valence shell is the 1s orbital. And so let's remember 1s orbital, what that looks like. And it is essentially just a sphere. So all of the s orbitals are a sphere. And the 1s is the smallest one, so closest to the nucleus. Okay, so we think about all that as we draw the molecular orbital diagram. The diagram is drawn on an energy scale, so we have higher energy at the top, lower energy at the bottom. And this is especially important when there are multiple valence shells, and we'll do an example later with a molecule where the atoms have more than one valence shell. But here for dihydrogen, we are just working with, I'm actually even going to make this arrow a little smaller. We are just working with the 1s orbital. So we say we have one of our hydrogens has a 1s orbital, and as I said earlier, it has one electron in that 1s orbital. The molecule has two hydrogens as part of the molecule, so we do the same thing for the atomic orbital, atomic 1s orbital of the hydrogen. And so far, we have not drawn any molecular orbitals. We've only arranged the atomic orbitals on this energy scale. Now we'll think about having two 1s orbitals. As long as the electrons are in the same phase, and that's often demonstrated with shading, then the 1s orbitals from each individual hydrogen atom will overlap and they will form a molecular orbital. Now, molecular orbitals are always lower energy. Bonding orbitals are always lower energy. And so we can show that the 1s orbitals overlap to form what we call a sigma bond. So if we have the 1s orbital from one hydrogen overlapping with the 1s orbital from another hydrogen, we have this valence shell overlap, which we can call a sigma bond. And then we have a sigma molecular orbital. It's possible that the electron from one hydrogen can be in phase, and then the electron from the other hydrogen we say is out of phase, and we can denote that by not shading the 1s orbital. And these two 1s orbitals now cannot overlap, and so we call these can then create an anti-bonding orbital, which is higher energy than the atomic 1s orbitals, and we denote that as a sigma star. So here we have a bonding molecular orbital. And here is an anti-bonding molecular orbital. Anytime you're creating a molecular orbital diagram to determine what molecular orbitals exist for a molecule, you'll always know if you have the right number of molecular orbitals by counting the originating atomic orbitals. When we have the dihydrogen molecule, we have two 1s orbitals that are overlapping. So we start with two atomic orbitals, one from each hydrogen. You should always have the same number of molecular orbitals. And in this case, we have two. We have a bonding sigma molecular orbital and a sigma star antibonding molecular orbital. So two molecular orbitals. Now we're almost done here. We just need to draw in the electrons into the molecular orbitals. And so we will follow these principles that I have typed out at the bottom of the page here. Just like I just said, if you start with two atomic orbitals, you should have two molecular orbitals. The same is true for the number of electrons. So however many electrons are present in atomic orbitals should also be present in the molecular orbitals. So I'll use a blue pen to show where the electrons end up when we draw the molecular orbital diagram. So we know we're going to be adding two electrons somewhere in the sigma and sigma star molecular orbitals. The Aufbau principle right here says that electrons occupy available orbitals with the lowest energy first. So we're going to put electrons into the lower energy orbital, which is the sigma orbital, before we occupy the sigma star. So when you're filling in electrons in your molecular orbitals, you just start at the bottom and work your way up, lowest energy to higher energy. Now, if I were to just right away copy over those two electrons the same way I drew them in the atomic orbitals, we do run into an issue when we look at Pauli exclusion principle, which has two electrons with the same spin. We represent spin as an arrow with half of an arrowhead pointing up or an arrow with half of an arrowhead pointing down. Two electrons with the same spin cannot occupy the same orbital. So in the molecular orbital for H2 for dihydrogen, one of the electrons is shown as spin up and the other as spin down. So we have two electrons in the sigma bonding molecular orbital. One has spin up, one has spin down. Hund's rule doesn't really apply here, but we will get to an example where we need to look at Hund's rule. Now the other thing we can do with a molecular orbital diagram is calculate the bond order. And this tells us information about how strong the bond is between the two atoms. We calculate bond order by taking the number of electrons in bonding orbitals and shorten orbital as orbs. We subtract the number of electrons in antibonding orbs. And we divide that number by 2. So the dihydrogen molecule bond order is number of electrons in bonding orbs, or orbitals, which is 2, minus the number of electrons in antibonding orbitals. We have 0 electrons in the sigma star orbital, and then we divide that by 2. So this gives us a bond order of 1. Now, typically this aligns with what we would expect for a Lewis structure, which it does for this molecule. If we think about drawing dihydrogen, since each hydrogen atom brings 1 electron, there is a single bond between the 2 hydrogen atoms, so we have a bond order of 1 that represents a single bond. Let's do an example with helium. Now, helium is a noble gas. It's not very reactive. But let's just say we have helium-2, dihelium, in a molecule. Let's see what that molecular orbital diagram would look like. Helium is also in the first row, so its valence shell is the 1s valence shell. We have 2 heliums in the molecule. So we draw 2 heliums as the individual atoms in the molecular orbital diagram. And then helium is in the second, not really the second column, but it has 2 electrons in its 1s valence shell. It's the second element in the first row. So that means it has a full 1s valence shell. Now remember, we have 1 electron spin up and the other spin down. These 1s orbitals can overlap to form a sigma molecular orbital and a sigma star. So we have 2 molecular orbitals, the sigma and the sigma star. We have 4 electrons that we need to fill in molecular orbitals. So now we have 2 electrons in the sigma molecular orbital. That's the greatest number that can fill that orbital. So we have to put the remaining 2 in the sigma star. Now when we calculate bond order, remember we do number of electrons in bonding orbitals, so that's 2, minus number of electrons in antibonding orbitals, that's also 2 for dihelium. Divide that by 2 to follow the formula. We have a bond order of 0. So there's no bond. Even if we tried to put 2 helium atoms together, they cannot bond to each other because we have the same number of electrons in the bonding orbital as we do the antibonding orbital.